introduce you and then you can then. Okay, welcome everyone to this week's QTFMS talk. Today we are delighted to have Lorenzo Di Pietro from University of Trieste. He's going to talk about his recent paper on boundary F-theorem, quantum field theories and AdS. Lorenzo, thanks a lot for agreeing to give a talk. It's a pleasure to have you. You can take it away.
Okay, thanks a lot, Burak, for having me. It's a pleasure. And yes, so today I will tell you about this recent paper. And please stop me at any time if you have questions. Okay, so the topic of this paper, as you see from the title, is some observable that we define in quantum field theory in AdS. So in my talk, what I'm going to do is in the beginning, I'm going to give some introduction of why I'm interested in studying quantum field theory in anti-de Sitter space and give some examples that motivate me to study this setup. Then only in the second part I will, so this introduction will take quite some time. And then after we do that, I will move to this observable that is in the title, which is the AdS partition function. And I will tell you about some conjecture that we have that this thing is monotonic along boundary energy flows. And I will tell you about some checks that we can do. Then in the third part, I will apply this conjecture to some interacting theories like long-range Ising and some two-dimensional models. Okay? So let's start with the motivation. So why am I interested in quantum field theory in anti-de Sitter space? And okay, one way to summarize it is that the idea is to use the boundary of AdS to try to learn about massive quantum field theories that we put inside, okay? And this philosophy, we can, in a sense, trace it back to this paper, which is one of the papers that started the modern revival of S-matrix bootstrap. Okay. So let's describe a little bit what is the problem. So the problem is that we want to study a massive quantum field theory, okay, which means that we have some RG flow. And the typical setup we encounter is that we have some ultraviolet description. This is very common, in which we have some coupling and we can do some perturbative expansion when the energies are large because our coupling has some positive mass dimension, and then we can expand in this ratio. Let's say this is some positive power of the energy. But then as we flow to larger and larger distance, at some point we hit strong coupling. And so it's very hard to learn about the observables in the IR, okay? So, of course, this is a very common setup, for instance, in QCD. And the problem one would like to solve is to find some efficient way to get some control over the microscopic IR observables, such as, for instance, scattering amplitudes or the spectrum of particles, okay? And so this is a very general problem, of course. Now, I want to study this problem on a very specific geometry, which is the geometry of Euclidean anti-de Sitter space, or if you wish, hyperbolic space. So just to set up the notation, this is I'm mostly going to use these Poincare coordinates for anti-de Sitter, in which the metric looks like this. So these coordinates are such that z is positive, and the conformal boundary of anti-de Sitter space sits at z equals 0, okay? So it's at infinite distance from any point inside. And then we have this flat slicing, so with the coordinate x, that parameterize some RD slices of our space. And so this is, of course, AdS d plus one dimensional. And L is the curvature radius of the space. So what are the advantages of setting up this problem on this background? So one nice thing is that you have this additional scale, okay, which is the curvature radius. This means that you gain a new dimensionless parameter. Okay, remember before we had this coupling G, which was dimensionful. and we could only use it to expand when we are at very small distances. Now we have an additional dimensionless parameter, which is a combination of the radius of AdS with my coupling, okay? So now I can also expand in this object. So far this is not so special, okay? I could use the same words in any background that introduces some length scale in my problem. For instance, I could also put my theory in a periodic box, and the same logic would apply. Also, if I put my theory in a torus, I could study, I could, I would gain this dimensionless parameter. However, one big advantage of anti-de Sitter is that it's much more symmetric than, for instance, a torus, okay? So it's a maximally symmetric space, which means that the number of space-time symmetry generators that you have is exactly the same as the ones you have in flat space. So you introduce a radius, you introduce a scale and a new dimensionless parameter in the problem, but you introduce it without paying any price in terms of space-time symmetries.
Can I ask a question?
Of course.
So let's say we have some conformal filter on a flat space, which has no
Mhm.
length scale at all. If we place this conformal filter on AdS, is it
Mhm.
going to be no longer CFT because we have this length scale?
So what happens is that if you study a conformal field theory on this background, so what is true for conformal field theories on curved space is that they only depend on the conformal structure of the metric.
Hmm.
So you see, it's not going to see this
Ah,
factor of g squared. So it's
hmm,
going to be exactly the same as studying the conformal field theory on half flat space. Okay?
hmm,
So you get something
okay.
which is called boundary conformal field theory. So it's a CFT
Hmm,
with a boundary, and if you place it in AdS in such a way to preserve the isometry of the background, automatically this is going to describe some what is called conformal boundary condition for your CFT. So
hmm,
a boundary condition that preserves a group, which is in this case of AdSD plus one, SO um, eh, SO1D plus one, okay, which is exactly
hmm.
the isometry.
Okay. And then we can also do the same story about like primary operator will represent us in the boundary,
Yes,
exactly
yes.
as in flat
You
space.
always have operators on the boundary that are like they form a structure similar to a d-dimensional conformal field theory. From the point of view of boundary CFT, this is always the case, and you can also view them as operators that live at the boundary of AdS if you interpret
Hmm.
the background as AdS.
Okay. And then I remember you were saying that there's no conserved Swiss energy transfer on this boundary CFD.
Are you asking us specifically about the case of the CFT, or you're
Oh,
asking
in general.
in general? Yes, yes. I'm gonna comment on that in a
Hmm.
second.
Okay. Thank you.
Did I answer the question? Okay. So yes, so as we said, so it's maximally symmetric, but then you could also say, okay, but then why you want to study this weird hyperbolic space? Why don't you do it on the sphere? No, the sphere has both of these properties. It introduces a radius, and it's also maximally symmetric. The advantage of hyperbolic space or anti-de Sitter space is that it also has an infinite volume, which means that there are phenomena like symmetry breaking and phase transition that are interesting field theory phenomena that depend on having an infinite volume, which you can still observe in this background, while it would be hard to see them on the sphere. On top of that, there is a notion of infinity in space, which is this conformal boundary, which you wouldn't have on the sphere. The fact that you have this notion of infinity in space allows you to define asymptotic observables, which are a bit similar, analogous, maybe I should say a Euclidean version of the scattering amplitudes in flat space. Okay, so this is what I just said. So if we study this quantum field theory in this background, we have the possibility of inserting local operators at the conformal boundary, okay, which is like infinitely far away from the point of view of a person living inside AdS. And thanks to the isometry SO1D plus 1 of my geometry, this isometry acts on this conformal boundary precisely like the conformal group. So these correlators are covariant under this symmetry. So if you want, you can use these words and say that these operators form a boundary CFT, okay? These words must be used a little bit with care. I mean, it's not like it's an independent theory. There is no independent definition of this theory at the boundary. It's just a subsector of the observables of my QFT, okay? But this subsector of observables among themselves, they form a structure which is completely analogous to that of a d-dimensional conformal field theory. Okay? E so as you might know from CFT, like usually we like to discuss CFTs in terms of their data, like the scaling dimensions, the OP coefficients. These are the typical observables. So you can ask, okay, but now what defines the data of this conformal field theory that lives at the boundary of my quantum field theory in AdS? Well, for sure, in order to fix those data, what you need to do is you need to specify the couplings of your quantum field theory. So for instance, this dimensionless parameter that we talked about before, we need to fix it. For each value of this dimensionless parameter, the data will change a little bit, okay? So it will depend on this. Interestingly, this is not enough to completely fix the data, okay? Even if you fix completely the bulk Lagrangian, let's say, or the value of the bulk couplings in units of AdS radius, you still have typically a discrete choice, which is the choice of how your fields behave at infinity. Okay, in other words, a choice of a boundary condition. Okay, so for every fixed bulk Lagrangian, we still have typically a discrete set of possible boundary CFTs, which depend on a choice of boundary condition. Okay. So it's important at this point, many of the words that we used are completely analogous to when we study AdS-CFT, which some of you might be familiar with. And it's important to distinguish the two setups, okay? So in this case, we don't have any dynamical gravity inside AdS, okay? So we just have a rigid quantum field theory. The metric is fixed, it doesn't fluctuate. We don't path integrate over the metric or anything like that. So this means that at the boundary, we will not have a stress tensor operator, okay? That is what Burak was mentioning before. And moreover, you shouldn't think at all of this as some sort of duality between the bulk quantum field theory and the CFT. This is what we think about when we do the CFT. Here it's completely different. We are not saying that, in a sense, this boundary CFT completely captures all the observables of the QFT. We are just saying that this is a subset of the observables, okay? So this is a subset of the possible observables of the quantum field theory, and we want to study it because it's nice, because it has conformal symmetry, okay? And we can use the power of conformal symmetry to constrain it. Is it clear? Okay. If you have questions, stop me. So now the idea is that then we can use this CFT approach to the dynamics of massive quantum field theories. And the idea is the following. So here I drew a cartoon of the AdS space as a function of this dimensionless parameter. Okay, so when this dimensionless parameter is big, I'm at strong coupling, and my AdS is big. And when instead this parameter is small, I'm at weak coupling, and AdS is small. So what do? We start by setting out the problem when AdS is small, okay? Of course, the fact that it's small when the coupling is weak when AdS is small is because I'm assuming that the theory is asymptotically free. No, I've started with a free UV description. So when AdS is small, this means that we are controlled by the macroscopic degrees of freedom, which are weakly coupled. And now here I can study my theory. I have full control. I can study what are the possible boundary conditions. And I can try to understand the properties of the corresponding boundary theories, boundary conformal field theories. So what are their symmetries, for instance? What are so by MFT, I mean mean field theory limit. So typically if we have some free fields in the bulk, the boundary theory is going to be described by some what is called mean field theory, which means just another word that is used for is generalized free theory. It means just some operators whose correlation functions are controlled by weak contractions. So you can try to understand what type of mean field theory you have at the boundary. And then what is the light spectrum? What are the light operators and their data? And then you can go a little bit also, you can turn on a small coupling and compute perturbatively the data of the boundary conformal field theory, the scaling dimensions, the OP coefficient. So this, you can do it with full control. And then, of course, your goal is to somehow connect to the flat space, which is what we're really interested in. For us, this curved space is just a tool. So what you would like to understand is all these boundary conditions that you find at weak coupling, which of them survives? Perhaps some of them disappear as we crank up the coupling. It's not for each value of GL, we might have a slightly different set of boundary conditions. So you want to understand what is the fate of the various boundary conditions in the flat space limit. And if you find some boundary condition that continuously extrapolates to flat space, in principle, you would like to be able to use it to extract the flat space data. An example is, suppose I have some dimension of some operator in my boundary theory, and I follow it as a function of GL, and if I see that this dimension goes to infinity linearly in the radius of AdS, the coefficient of this radius tells me about mass of an excitation in my flat space theory, okay? This is the usual relation between the dimension and the mass, just expanded when delta is large.
I have a question.
Yes.
If you have a supersymmetric quantum field theory on AdS, do we have the notion of envelope exactness, and then maybe using that we can extract some robust information for the flat space limit?
Mm. Yeah, so certainly you need some tool in order to be able to have control over the whole range. Supersymmetry can be a tool. You need maybe more supersymmetry than what you think, in the sense that, for instance, if you study in 4 dimensions, you need at least n equals 2 in order to have some protected observable, because the boundary condition, the fact that you introduce this boundary breaks half of the supersymmetries. So for instance, if you would start from 4D n equal 1, the kind of supersymmetry you would have is just 3D n equal 1. So it would not be enough to have holomorphy, for instance, or some kind of protection that usually you have from supersymmetry. So if you instead have 4D n equals 2, then on the boundary you will have 4D n equal 1 and is much more protected. Sorry, in the
Mm.
boundary you have 3D n equals 2, I wanted to say. And then this is much more protected and you can use it to try to extrapolate.
Yes.
But yes, so in general, here you need some non-perturbative method to really go all the way. And one possibility, for instance, is to try to use the numerical conformal bootstrap. And this, in some case, it was done. I will mention it before. I will mention it later. But for instance, the conformal bootstrap here is available to us because we have conformal symmetry. Okay, so we can try to use. Okay, if you don't know what it is, it's not so important. But I just wanted to mention that there are some non-perturbative tools that we can use. Okay, let me mention some important examples. So one example is gauge theories. Of course, that's an important case of a massive quantum field theory that we would like to understand better. So for instance, starting from this paper by Callan and Wilczek in the 1990, people have studied Young Mills on the background of AdS-4. And okay, so let's try to apply this philosophy that we mentioned here. So first we study a weak coupling and we ask ourselves, okay, at weak coupling, what are the possible boundary conditions for Young Mills? And one boundary condition is Dirichlet, which takes this form, which means that the gauge fields go like, they define a boundary current operator. And this boundary current operator means that you have a global symmetry with the same group as the gauge group at the boundary. And this current has protected dimension 2. Another possibility is that you study impose Neumann, which means that your gauge field goes like defines a three-dimensional gauge field at the boundary. Okay, so in this case, the gauge group is still gauged also at the boundary, so you don't have any global symmetry. I mean, you don't have any G on Mills global symmetry, I meant. Okay. Now, what do you expect at strong coupling? Well, at strong coupling, you expect to have color confinement. So you expect that the asymptotic states should not be charged under the color group. Uh, and this means, I mean, this is a bit at odd with the Dirichlet boundary condition, right? Because this Dirichlet boundary condition gives you this color group at the boundary. So this was observed in this very nice paper from 2012, in which they said that there is some clash between this expectation and the Dirichlet boundary condition, which suggests that as we increase, so this lambda L now is the Young-Mills scale in units of the radius of AdS. So at some point, as we increase it, we should have some transition in which the Dirichlet boundary condition disappears. So we go from a deconfined phase, deconfined because we have this color group at the boundary, so it's like we can see gluons asymptotically. Okay, so this is a deconfined phase, and then at some point we should transition to a confined phase because we expect that to be realized in flat space. Okay. And instead, with Neumann, not necessarily we expect any transition because Neumann doesn't have any color charge at the boundary, even at weak coupling. So the Neumann boundary condition instead is expected to be continuous all the way.
What happens for U1 gauge group in the Dirichlet boundary condition case?
Yeah, for
Because we
U1 it's a
expect
little bit less
deconfined.
clear because U1 is a bit different from the setup we had at the beginning in the sense that in 4 dimensions U1 is free in the IR. Instead of being weakly coupled in the UV and then flowing to strong coupling, it's the opposite, no? It becomes
Mhm.
it's weakly coupled in the IR and you need to UV complete it in the UV. So the setup is a bit, but maybe you can ask the same question about U1 in 3 dimensions. In three
Mm.
dimensions, U1 is also asymptotically free, like it's free. And
Mhm.
then I think, uh, well, if you just have U1 by itself, it's just a free theory, it's just a scalar, so it's not so. But you can ask this similar question about QED in 3 dimensions. And hmm, yeah, okay, sorry. The answer is that actually in 3 dimensions, the Dirichlet boundary condition is a bit problematic. So in a
Mm.
sense, it doesn't exist even with coupling. So it's already, yeah. So all in 4 dimensions, you have this interesting
Okay.
behavior.
But why exactly is it problematic? Like
Well, the
in
technical
3D?
answer, maybe there is a simpler way to say which is less technical, but technically I understand it like this. If you do exactly the same in 3D, uh,
Hmm.
this object is going to have dimension, the boundary is going to be two-dimensional. This object is going to
Hmm.
have dimension one instead of two. But then
Mm.
what happens is that the operator JJ, which makes sense at weak coupling, it has precisely dimension 2, which is the same dimension as the boundary dimension. And so
Mm.
it's an operator which is marginal, and this means that it has a beta function. Uh,
Mm.
okay, so it's a bit hard to satisfy that this boundary condition preserves the DS isometries.
Mm. I see, I see. Okay.
Maybe it's going to become a bit more clear in a second when we mention about how the Dirichlet disappears.
Mm.
Okay, so now we need to somehow make sense then of how to reconcile the weak coupling finding with the strong coupling. Okay, so in the proposed extrapolation, so the proposal for what happens in the middle is that as we increase the coupling, at some point, the Dirichlet boundary condition, there is this phenomenon between in CFT which is called merger and annihilation. Okay, so it means that two CFTs, if they uh, become the same CFT in a way that I will make more clear, they can then disappear. Okay, so the idea is that as we are at sufficiently strong coupling, there is another boundary condition that we call D star that merges and annihilates with D and makes it disappear, while the N, I mean Neumann, extrapolates continuously to flat space. Okay, and in some work that we did, we found some perturbative indications that this is the correct mechanism, and it is also favored by numerical conformal bootstrap. Now, let me try to explain a little bit better what this means. So what this means is that there is an operator at the boundary, which is a singlet under the GM-Mills global symmetry. And let's call Y the coupling associated to this operator. Okay. Then what we're saying is that if you are at coupling smaller than this lambda L critical, the beta function for this coupling has this form, okay, as you see here on the left. And then there are two fixed points. One fixed point is attractive and is called D. And there is this repulsive fixed point, which at the moment is still a little bit mysterious what precisely is its nature, which is called D star. Okay, and then this D star on one side, if we turn on Y with one sign, it flows to Dirichlet, and if you turn it with the other side, it flows to Neumann. And then as you increase to coupling larger than this critical value, what happens is that you see the parabola goes up until these two solutions merge and become complex. So after that, the Dirichlet and the Dirichlet star boundary conditions stop existing. Okay, so that's the mechanism that we believe to cause the disappearance of the Dirichlet boundary condition. Okay, so this is nice because somehow it tells you how the naive picture with gluons disappears in a gradual way as we increase the radius of AdS. Okay, questions about this? So I just want to stress that you see it's very important that here we have this RG. It's going to be important for the following that we have these RG flows between Dirichlet and D and between Dirichlet star and Dirichlet star and Neumann, okay? Which is what I depicted here with these arrows and here with this coupling Y, okay? Okay, now I'm going to mention a second example, which is the Einstein model in ADS2. So this is a theory of scalars that live on a sphere, parameterized sphere. And this is also a theory that is asymptotically free, okay, famously develops a mass gap. Okay, so even though naively it looks like a theory of free massless scalars, not free, sorry, naively it looks like a theory of massless scalars, but quantum mechanically these scalars develop a mass. So the simplest boundary conditions for this theory at weak coupling are a Dirichlet boundary condition that preserves the ON symmetry, okay? That breaks the ON symmetry, which means that we fix at the boundary one particular direction in which our scalar field points. And in this case, the fluctuation of our scalar field is a marginal operator. Okay, it has dimension 1. It's like a Goldstone boson. It's an operator that corresponds to a massless field. Okay. And this marginal operator parameterizes a conformal manifold, which is the sphere, which is precisely the space of aqua of our theory. Okay, so it's a general phenomenon that when we have spontaneous symmetry breaking in AdS of a zero form symmetry, this corresponds to some conformal manifold in the boundary CFT. Now, another boundary condition that exists at weak coupling is a ON preserving boundary condition, in which instead the scalar field phi doesn't go to a constant, okay? Doesn't go to a constant like we had here. It goes just to an operator of some dimension delta. And this dimension delta is fixed in terms of the dynamically generated mass, okay? And okay, you can distinguish if you want, it's a bit semantic, this distinction, but you can distinguish a Dirichlet or a Neumann. You can call this boundary condition Dirichlet or Neumann depending on whether the scaling dimension is larger or smaller than 1/2. So I should mention that these two, you see, I'm already including finite coupling because I'm already including a dynamically generated scale. So this is because I'm solving this theory at large n. Okay, so when I say weak coupling, I really mean leading order in 1/n. Okay? Uh, Now, again, you can ask yourself, what do you expect at strong coupling? And then at strong coupling, we expect that in two dimensions there cannot be spontaneous symmetry breaking, okay, which is what we said before, that this model develops a mass gap. So it should happen that the spontaneous symmetry breaking boundary condition that I mentioned here, the first one, should disappear. So you see, this is a toy model for what we saw before for Yang-Mills. Here we have this spontaneous symmetry breaking boundary condition and somehow should disappear when we go to large radius, and we should have only a gapped OM preserving boundary condition. Instead, if we impose the symmetric boundary conditions, they can be completely continuous. Okay? Again, what is the picture here for the extrapolation? Just a bit, we can go over this a little bit faster, but the idea is very similar. The idea is that we have two boundary conditions. The symmetry preserving one is the line above, and here it is the symmetry breaking. At some point, the symmetry breaking must disappear. Here, it's a little bit different, the mechanism. What happens is that you see this conformal manifold that exists in every symmetry breaking boundary condition somehow becomes smaller and smaller, and at some point it merges. So this sphere of conformal field theories becomes of reduced zero, and it merges with the symmetry preserving boundary condition. And another advantage compared to Yang-Mills is that in this case, actually, this we can completely prove at least at leading order at large n, because the theory is solvable in the large n expansion.
Can I ask a question?
Yes.
So in two dimensions, a boundary is like a one-dimensional thing, so it's we
Mhm.
can regard it as like a line defect on this 2D. So this
Mhm.
disappearance of the Dirichlet boundary condition means like we cannot insert line defects on this one model, right?
Yes, I mean, it means that this particular boundary, or this particular, if you want to think about it as I mean, it's more like in this case, it's really a boundary, right? Because on the other side, there is nothing.
Hmm.
You cannot, for a sufficiently large AdS, you cannot have it with a fix, with the scalar, with the bulk scalar approaching a constant value. It's just not possible. Because you see, if you would do it for a very large AdS, it would mean that you get close to having scalars in flat space that approach a constant value at infinity. But we know that for massless scalars in flat space, there are large logarithmic fluctuations that forbid you to fix the
Hmm.
value at infinity. Okay, so here we are
Hmm.
just seeing that this thing is impossible if AdS is
Hmm.
large.
I see, I see. Okay.
And
It's
it's a
like
bit of a toy model
okay,
for the disappearance of Dirichlet and Mills, which is more under control. Okay.
I see. Okay, so this is like the two-point function of phi being like logarithmic in
Yes,
three
I mean, in AdS
dimensions.
it's never
That's
logarithmic, okay? In AdS it's never
Mhm.
logarithmic because there is always L, which
Mhm.
let's say regulates this logarithm. But
Mhm.
you see it gradually. You see gradually.
Hmm.
So that's why in AdS it's possible to have the symmetry breaking boundary condition. But the
I
symmetry breaking
see.
boundary condition at some point must disappear. And this.
Okay, okay, okay.
And I just want to say that also here it's important that we have RG flows that connect these different boundary conditions. Just as we saw before, we had Dirichlet star with RG flows to Neumann and Dirichlet. Here we have RG flows between the symmetry preserving boundary condition, which exists all the way until flat space, and the symmetry breaking one. And this is a very simple RG because you can just turn on the an operator that is charged under the symmetry, and if you turn it on, the boundary condition breaks the symmetry now, and so you flow from the symmetry preserving to the symmetry breaking boundary condition. Okay. Indeed, this tells you that this this symmetry breaking boundary condition is expected to exist as long as this operator is relevant, because you can flow from up to down. Okay, and then at some point it stops. Okay, so this was a bunch of motivating examples, and an important lesson that I want to draw from this is that in both of these examples, we had an interesting structure of different possible boundary conditions and RG flows between them. Okay, so this is going to be the motivating aspect for the second part of the talk. So now I'm gonna switch to talk about the observable that we introduced in this more recent paper. So yeah, as I said now, the crucial ingredient to understand the strong coupling or large radius behavior in the examples we saw before was the existence of these boundary energy flows between the various boundary conditions for a fixed theory. So I fix the theory in the bulk, and then I have this set of boundary conditions and possible energy flows between them. Okay? And the dynamics of this boundary energy flow tells me about what can happen as I go to strong coupling. So this motivates to understand in what cases flows between boundary conditions are possible. Okay? And so we are used to the idea that in quantum field theory, there are powerful tools to put constraints on possible normalization group flows. And this is the existence of quantities that are monotonic under RG flows. Okay, so for instance, it's very famous the C-theorem in two-dimensional quantum field theory, or the A-theorem in four-dimensional quantum field theory that tell you that there is some quantity that can only decrease. So in general, the structure of this kind of theorems is that we have some function that associates some number to the set of conformal field theories. And then if an RG flow exists between the two conformal field theories, then this quantity is larger in the UV than it is in the IR. And it has an interpretation of counting the number of degrees of freedom. And I just want to point out that typically, if you also consider supersymmetric theories, at least with sufficient number of supersymmetries, it's always the case that this quantity is also the one that you use to determine the superconformal R symmetry in the superconformal fixed points by extremization. Okay, so this started with the A maximization of interrogator on back. This is a bit of a technical comment, so if you don't know what I'm talking about, it's not so important, but I want to make it because it was what motivated us to introduce this quantity. So just as a curiosity. So now, in this work, what we do something similar, but for this set of possible boundary conditions. So instead of now defining a quantity for each local conformal field theory, like in the famous examples we saw before, we're going to do something much more restricted, which is to say, given a fixed quantum field theory in anti-de Sitter, with fixed masses, fixed massive couplings, I'm going to define a quantity that takes all the possible boundary conditions and it spits out a number for a given bulk theory. And we propose that this quantity is monotonic along the boundary energy flows between the different boundary conditions. So in a way, it gives us a way to put an order in all the possible boundary conditions and say, okay, you can go from this to this, but not vice versa. Okay? And so as I was saying a second ago, this was suggested by the fact that we studied supersymmetric theories. And in the supersymmetric theories, we found that there was this quantity that we needed to use to extremize and find the superconformal R symmetry. But then, since this never fails to be also a monotonic quantity along RG flows, this suggested to us the idea that it should be also a monotonic quantity. And it's also suggested by, okay, Burak at the beginning asked me about what happens if I put a CFT in AdS, and I said that this is a boundary conformal field theory. So for boundary conformal field theory, it is well known that there is a monotonic quantity that decreases along boundary RG flows between different conformal boundary conditions. So if you want, our proposal just extends from the case in which the bulk is conformal to a generic massive bulk, okay? To a generic massive bulk. So this was a proposal by Giombi and Canciandani. So roughly speaking, this quantity we define it by just taking the theory, computing the logarithm of the partition function in AdS with some sign in front. Okay, you need to put some sign because depending on the dimension, it changes. Now, if you want to be a little bit more precise, you need to describe how you're going to regulate various divergences that you encounter when you do this computation. Okay, so that's what we're going to do now. So this quantity is both IR divergent and UV divergent, okay? So the IR divergence is due to the fact that we are working in this infinite volume space, okay? And the way to deal with them is with the same procedure that in the context of AdS-CFT goes under the name of holographic normalization, okay? So what you do is that you do the computation with a fixed cutoff in the radial direction. Let's say z equals z naught, okay? And then you need to be able to reabsorb all the divergent contributions you find in a redefinition of local couplings on this cutoff surface. And when we try to apply this procedure for just the AdS partition function, depending on whether the dimension is even or odd, we are going to encounter a universal term, which is either the coefficient of the log of this cutoff or a finite term, okay? So this is more precisely what we mean by this log z. We mean that we put this cutoff, then when we take it to 0, we are going to encounter either a finite term or we're going to encounter a log z. And you can check that these things are universal, and this is what we define to be the partition function. Another way to say what I'm saying now is that we are computing a free energy in a space with infinite volume, and we are regulating the volume of AdS, okay? The volume of AdS can be regulated, and in some dimensions, it gives you a finite term. In some dimensions, it gives you a log with a universal coefficient. Then another thing that you need to be worried about are UV divergences, and the UV divergences are going, I mean, they are the same as you would have in flat space, and they're just given by the usual coincident points singularities. And these need to be subtracted using instead bulk counter terms. Okay, and the typical type of counter term, since we are just computing the free energy and the only source that we have turned on is the background metric of AdS, so they can only take the form of an integral in AdS of some curvature with some power of the UV cutoff and some power of my coupling, okay? That's the typical counter term. But now, when you integrate the counter term on the background, what you're going to get? You're going to get a volume of AdS, you're going to get some power of the radius, and your UV cutoff. So the important thing is that these guys are independent of the boundary condition, okay? Because they're just given by local divergences in the bulk. So now, how do we deal with these UV divergences? We can deal with them in two ways. So one way, using the observation I made a second ago that they're independent of the boundary condition, you can decide that you stop asking yourself what is this quantity f for any single boundary condition, but you just ask about differences, okay? Because at the end of the day, monotonicity means that the difference is positive between two boundary conditions. So if you consider the difference, these UV divergences are going to cancel because they're going to be the same for both boundary conditions, okay? So this is one way. Another way to phrase the same solution is to say that we sacrifice one boundary condition. So one of them uses a reference, and for all the others, we define just this difference to be our AdS partition function. Another thing that you can do is that a little bit more sophisticated, you can use this observation that they all have this, all the counter terms come from this curvature. But then you can say, okay, what about if instead I would put my theory on the sphere? Well, I will have exactly the same UV divergences, but now this R will be the curvature invariant on the sphere, okay? And the only difference will be the sign. So what I can do is that I can take my AdS partition function and I can subtract the sphere partition function, but by doing an analytic continuation with the radius that goes to IL, okay, in such a way that I precisely cancel the contribution from the AdS counter term. So if you want, you can also do this, and also this is going to give you a finite quantity. Indeed, in BCFT, this is typically when people define this free energy, this monotonic quantity for BCFTs, typically what they did is that they took the partition function on hemisphere or a partition function IDS divided by the partition function on the sphere. Okay, so when you take the logarithm, you get this kind of difference. In that case, they didn't have to discuss this weird I continuation of the radius, and that was because they didn't have massive couplings, so only some particular powers of R appeared, and so it didn't require to use the I.
So this, yeah,
Mhm,
like, is it like a rig rotation or another continuation of the sphere radius
mhm,
that's setting R equals to IL?
mhm,
And if you were using like Lorentzian AdS and you were to define this quantity, the F function,
mhm.
you would not need to use like R equals to IL, or would you still need to, need to decontinue the radius?
No, it's not an issue of Lorentzian versus Euclidean. I mean, in order to define partition function, typically it's always better to work in Euclidean, right? So that we have some definite Riemann geometry that we can study. It's more like that one has positive, constant positive curvature, and the other one is negative,
Okay.
constant negative curvature. And since all the divergences are proportional to a power of the curvature, this is just a simple trick that you can use to cancel them. Because
Hmm.
you see, all the curvature are going to be powers of 1 over r squared, for instance. And then by using this trick, I just change the sign in front. That's the
I
simple.
see, I see. Okay, okay, I see.
Okay. Um,
And also, for the first method,
yes.
you say like we choose a specific boundary condition as like a reference. But
Mhm.
how many possible boundary conditions you have, like, apart from Dirichlet and Neumann,
Yeah, I
for
mean,
example?
it's depends very much on the theory, and it's impossible to give a completely universal answer. But I'm just saying, uh, typically your question will be, I want to know if this boundary condition go to this other one. Then you can just, instead of obsessing in defining both of the quantities, you can just consider the difference, and you will not have a lot of problem with these UV divergences because they're gonna cancel.
Hmm. So it's like you're
Makes sense.
setting one of the boundary conditions as like a ground state that has a zero free energy.
Yes.
Okay.
Okay. Okay. Mm, so let's do a sanity check that because we want to propose that this quantity is monotonic, so it's better be the case that at least we can check it in the free theory. So let's check it in the free theory. So let's consider a bulk free scalar. So here we have two boundary conditions. You can call it Neumann or Dirichlet or plus and minus, which come from the two solutions of this equation between the mass and the scaling dimension, okay? So famously, phi will give an operator phi hat of dimension delta, but there are two possible solutions for delta given the mass. One is bigger than d over 2, and the other one is smaller than d over 2. One we call it plus, and one we call it minus, okay? So for a fixed m, I have two CFTs. Now, the picture looks like this. Now, as a function of m squared L squared, I have, so actually, if m squared squared is very large, only the plus boundary condition is unitary, because the other one is below unitarity bound. Delta minus becomes too small and is below unitarity bound. But then at some point, under this value, where BF means Berthelon and Friedman, under this value of m squared plus 1, we start having both boundary conditions. And then, precisely at the Bernoulli-Friedman bound, the two boundary conditions merge and annihilate and become complex, because below this, the scalar is not stable anymore. Okay? Um, and there is an RG flow. Okay? There is a famous double trace RG flow that goes from the minus boundary condition to the plus boundary condition by turning on this operator. You see, in the minus boundary condition, this operator phi hat squared has dimension smaller than d, so it's relevant, and it can flow to the other one. So we need to check that the free energy of minus is larger than the free energy of plus, if our conjecture is supposed to make sense. And indeed, this you can do. It's a simple calculation. So, for instance, one way to compute it is to take the derivative with respect to the mass of your partition function. And you see, if you take the derivative, this is going to give you the integral of phi squared, because m squared couples to the operator phi squared. So this is going to become just the volume of AdS plus 1 times the VEV of this operator. And this it's easy to compute. You just have to compute this tadpole, okay? And after you compute this, you get this derivative of the difference. And you need to fix an integration constant. And the integration constant, you simply see from this figure that the integration constant is going to be fixed by requiring that the difference is 0 at Bertalanffy and Friedman bound. Okay? Because they're the same at that point. And you can do it, and you completely fix this difference, and you see that it's positive. Okay? And you can do the same check for massive free fermions. And this is a picture of the differences for various values of the dimension. Okay? Here, the 0 is fixed to be a Bertalanffy and Friedman, and then I'm increasing the mass. Okay, so let me now move to the applications. I should mention that in the paper we also have another argument in favor of this, which is that we provide a proof in ADS2. Okay, but it was since the proof is a bit technical, I decided to skip it. But you can look it up in the paper. So let me just now tell you about the applications. So one application is to the long range icing. Let me explain what does this have to do with counterfiltering ADS, because it might be a bit mysterious. So, the typical QFT monotonicity theorems that we discussed before apply to renormalization. So the one on the C theorem, the A theorem, and similar things that exist in 3D, they apply to RG flows between local quantum field theory, local conformal field theories. Okay, sometimes I mean they've been extended also for defects within the local quantum field theory, but this is the setup. Now, there are also interesting models that are intrinsically non-local, okay? Like long-range models. And one of them is the famous long-range icing, which is a statistical physics model in which you consider an energy function which is similar to the one of icing, but instead of summing only over spins that are close, you sum over every couples of spins with a decreasing function like this, a power law decreasing function. Okay? And there is this parameter S that tells you how fast this power shuts down at long distances. And this is a nice continuum description, which is a continuous, as you might expect, similar to Landau-Ginzburg. It has phi squared phi to the fourth, but then the kinetic term for the scalars, instead of being a local kinetic term, is this kind of non-local one with the difference between x and y. And this means that your operator phi, instead of having the canonical dimension of a field, it has this dimension d minus s over 2. Okay? So if you now tune the parameter t to be at a second order transition, this is what describes the long-range icing conformal field theory. Okay? Okay, so far it's not clear what it has to do with QFT and AdS, but let me explain. So the nice thing is that you can realize this Lagrangian, you can realize it as an interacting boundary condition of the massive scalar field in anti-de Sitter. Okay? The reason is that, you see, we saw a second ago that the free scalar has an operator of generic dimension delta at the boundary, depending on the mass. Okay? And then I can just modify the boundary by adding this operator, lambda phi 4. Okay? And this is going to flow to the long-range icing CFT. So the long-range icing CFT is a boundary condition of a free scalar field in anti-de Sitter. Okay? So now, using what we just discussed in the second part of the talk, this means that I can assign a quantity f long-range icing, and I can use it to test RG flows that connect to the long-range icing CFT. So, for instance, in this paper of 2017, this kind of RG flows were considered. Let me explain a little bit. So there are two ways to obtain the long-range Ising conformal field theory in the continuum. One is the one that we described a second ago. So this means that we start from the minus boundary condition of the free scalar, and we turn on this phi minus to the fourth interaction at the boundary. And this red line deformed by the phi minus to the fourth, and it goes to this conformal field theory, long-range Ising CFT. Another possibility is that you can consider a different setup in which you start with the plus boundary condition for the massive scalar in anti-de Sitter, but you add at the boundary a decoupled local three-dimensional Ising, and then you deform by an interaction that couples these two sectors. The interaction that couples these two sectors is the product of the spin operator of the not three-dimensional, let's say d-dimensional Ising conformal field theory. You multiply it by the phi hat mode of your scalar field in anti-de Sitter, and so S plus S Ising is this green line, and this is the deformation that flows to also long-range Ising. Okay, this was discovered in 2017 that you can have these two different realizations if you wish dual to each other. Now, it's interesting that both of these constructions only work in a certain range of parameters, okay, which is when this parameter S is between these two limits. Well, if you go outside these parameters, what happens is that either if you go to two large values of S, what happens is that the red theory, instead of flowing to long-range Ising, flows to the green, okay? Vice versa, if you go to two small values of S, the green theory, instead of flowing to long-range Ising, it flows to the red one, okay? So that was, it's a very fast review of things that were discovered here. The details are not going to be so important for us, but you see that now here we have some checks that we can do. First of all, we can check that for this value, for this range of S, the AdS free energy of the red theory must be larger than the AdS free energy of the green theory. Vice versa, for this range of S, the AdS free energy of the green theory must be larger than the one of the red theory. And here in between, what we can do is that we can put some bound on what can be the free energy of the long-range Ising, okay? Because this, we don't have at the moment an independent way of computing it, okay? So let me describe this. So this is just putting the bound on the F of the long-range Ising. So we are able to say that this monotonic quantity for the long-range Ising must sit in this pink region as a function of S that comes from the inequality. See, we are imposing that it's both less than the red one and less than the green one. That's why the plot has this kind of shape, because what matters is the minimum between the two. And this is the result for d equal to. And now let me perhaps more interesting from the point of view of testing the conjecture. Let's see if these two are satisfied. And this is the plot. Okay, so there is a bit of a complicated rescaling to have a unique plot that works both in d equals 2 and d equals 3, but that's not so interesting just because we want to do one plot together. But you see here, the important thing is that this blue region is the one in which we flow to long-range Ising from both ends. And you see that before that, the orange line is always above the blue line, and vice versa, when we are on the other side, the blue line is always above the orange line, which is precisely the check of the two monotonicity for the two RG flows that we have at the two ends. Okay? So I should say that, yeah, this is, sorry, I said it wrong. Orange and blue just means d equals 2, d equals 3. These two plots, what they are the difference between the free energy of the red line and the free energy of the green line. Okay, so this means that this difference must be negative when I'm to the left of the blue region and must be positive when I'm to the right of the blue region. And you see that indeed both in d equals 2 and d equals 3, it is negative here, it is positive here. Okay?
Sorry, I'm a bit lost. Are these bootstrap results, like non-perturbative, or are these perturbative
No,
things?
I mean, you just
I
need to, F Ising is known. Okay, so what do I need to do this computation? I need to know the free energy of the plus and the minus boundary condition. These are just
Mhm.
results of free theory in AdS that I mentioned 1 second before, so we can compute them. And you need to know, so there is one bit which is in a sense non-perturbative, which is you need to know the F coefficient for the three-dimensional local Ising of formal field
Hmm.
theory. And this is known in 2 dimensions because it's just given by the central charge of the Ising CFT. And it is
Hmm.
known in 3 dimensions because with a certain precision, because people computed it with various methods, which are epsilon expansion and also fuzzy sphere. Okay.
Hmm. Okay.
So what I'm doing now is that I'm using these results to test the monotonicity of this F quantity defined for quantum field theory in AdS. Okay?
Okay, but what about the interaction term? Because
No, no, no,
that's
no.
what I'm
The
confused.
monotonicity doesn't care about the interaction is a deformation, right?
Oh.
That makes you have an RG. The monotonicity tells you that the
Oh, okay,
theory
okay, okay,
at
okay,
the
okay.
top
I see,
must
I
have
see.
a quantity that is
Okay.
larger than the theory at the bottom, okay? So
Okay,
if
okay.
you want,
Yeah, yeah.
maybe
I see, I see.
the interesting aspect is that these two quantities are very easy and
I
they're
see, I see.
computed by free theory, and somehow
Mm-hmm.
there is an inequality that relates a
Mm-hmm.
non-perturbative quantity, which is F coefficient for the Ising local conformal field theory. We discovered that it must satisfy some inequality related to these two quantities, which are completely free, I mean, free theory
I
quantities.
see, I see, I see, I see. So you don't have to
Okay.
worry about that. Now, I was a bit lost about that, but now it's clear.
Yeah, yeah. I mean, the RG, the fixed points are easy. What is difficult is the
Mhm.
RG itself.
Okay.
Okay. Maybe I can also since in view of time, I can just say, without too many details, that we also do the check for the two-dimensional sigma model that I mentioned before. Since in this case we have large n, we are able to actually compute in this interacting theory the F coefficient both for the symmetry preserving boundary condition and the symmetry breaking boundary condition, and we are able to test that the difference is as predicted by this RG flow. Okay, so we can check that indeed it's always larger until it becomes 0 at the transition point. Okay. Okay, so I can conclude saying what would be some interesting future directions. So, as I mentioned, we have a proof for this result in ADS2, but it would be nice to explore if it's possible to prove it in more general dimension. And another important thing is to apply to Yang-Mills. So what does this mean? So if this picture is supposed to be correct, one thing that this picture tells you is that you see very close to here, the f of Dirichlet must be larger than the f of Neumann, because you see that we have an RG flow between D star and Neumann, but here D star is merging with D. So we have a new way to test this picture, and the new way to test this picture would be to compute this f coefficient for Dirichlet, compute it for Neumann, and check that the inequality is satisfied. At the moment, this has not been done. It would be nice to do it. And that's all.
Thank you for the great talk, and for telling us about your work. Now we can have some questions. Okay, I have a couple of questions.
Mhm.
First, about this non-local model that you mentioned, the long-range Ising.
Yes.
So, there's no ordinary kinetic term for this, but it's like you have two phi fields and some propagator between them. Well, what kind of, like, do you have unitarity in this model, or
Yeah, I
is
mean,
it a
uh, in a sense, So how you can think about it is that this is just you start with a generalized free field, okay, which means you just have some scalar operator of dimension delta, and all the correlation functions are computed by weak contractions, and then you're turning on this quartic self-interaction, okay?
Hmm.
So there are some words to be used to be a little bit careful. So first of all, unitarity is going to be there if you choose delta to be unitary, in the unitary range to start with, okay? And also, these words that I just used only make sense if this phi to the fourth interaction is going to be relevant,
Hmm.
because otherwise you flow back to your GFF, okay? So, and this is precisely why we have this restriction that we have a restriction that the description that I just gave you only works below a certain value of S, because below a
Hmm.
certain value of S, um, below this value, sorry, they only work. I meant, sorry, above a certain value of S, because it can only work here because only here this coupling is relevant. Okay? So if you try to do it before this description doesn't work because the quartic interaction is irrelevant, and so you flow back to the red line. Okay? But now then another thing that can happen is that it can happen. So what we see from this picture, I'm basically reviewing what was discovered in 2017. If you make S too big, then you need to be careful because it could be that actually you don't flow anymore to the long range icing, but you flow to this different thing, which is a localizing. But that's related to the fact that, if S is too large, if S is very large, this decays very fast and the universality class changes. You're not anymore, you don't have anymore this non-local universality class, but you have a local one.
Hmm.
But I don't
Okay.
know if I answered your question.
Yeah, yeah, just yeah. I mean, it's a bit weird for me to see that action, but I
Which
guess
action?
that,
It,
yeah, disconnected term.
yeah, but I mean,
It's not even a kinetic
like
term,
this, you
but
can just view it as a massive scalar in anti-de Sitter in which you turn on this boundary condition.
hmm.
Makes perfect sense as well.
And also I want to check if I understood correctly. So the in the examples you gave, the long range Ising and the other model, you have an idea of what the star should be, right? Because, or did I get that wrong?
In which example, repeat?
In this 2D OM signal model and the long range Ising model, you have a pretty good idea of what the star should be
Well, I
in
mean,
the motility part, or is that not?
let me say, like here in the sigma model, so if you mean if I have a good idea of what makes this boundary condition disappear, yes, I do.
Mhm.
It's because I can do the computations non perturbatively at leading order at large n, and then I see that. But in this case, it's not super similar to. I mean, it's not like there is a this star that annihilates with this. It's more like this object, this boundary condition, was a family of boundary conditions.
Hmm.
Altogether, they disappear and they merge with the symmetric boundary condition. So, in a sense, there is no super close analog of this star in this setup.
Ah,
There
okay.
is also a boundary condition that disappears, and they understand why it disappears. Okay.
Hmm.
In the case of the long range icing, what is an analog of? I mean, also here you can say that this boundary condition, the blue one, only exists in some range of parameters. Uh, but yeah, also here we have a good understanding of why it only exists here and what happens at the two ends. So, in a sense, the most mysterious case is the one of Ian Mills, in which we
Hmm.
do believe that D disappears because of some D star, but at the moment we don't have a lot of uh,
Hmm.
very good
Okay.
understanding of what is this D star.
Okay, so there is no sharp analog of this in the two examples you mentioned.
Not super sharp. I
Okay,
mean,
okay.
if you want the sharpest analog is in the free scalar, in the sense that in the free scalar you also have the Neumann and Dirichlet that merge and annihilate.
Hmm.
But in this case, everything is understood, of course, because it's a free theory.
Hmm. I see. Okay, thank you.
No problem.
I don't know if there are any other questions. Just wait to find out a second. I think not. Then I'm stopping the recording. Thanks again.